Hi everyone. Let us continue our discussion of entropy and factors that affect entropy, including this idea of complexity. The first thing I want to go over, we'll go to this table in just a bit, but before that, let us define standard entropy. Standard entropy. The symbol for standard entropy is S with this naught or this zero superscript. It's the absolute entropy of a substance at 1 atm. And actually that is the only requirement. It doesn't have to be at 25 degrees, but most standard entropies are measured at 25 degrees C. But what else do you also notice? We're talking about the absolute value, S. It's not only delta S. So we notice that we can have S, and in previous videos and in the future videos, we're going to calculate and look at delta S. That's not the same thing for other thermodynamic parameters. Other thermodynamic parameters, that's what we call entropy, enthalpy, energy, thermodynamic parameters. There's no H, only a change in H. And there's no energy. Some textbooks, I like to use U, some textbooks use U or E. Energy. We don't have absolute energy. We only have a change in energy, a comparison between final and initial states. All right, so that's what we mean by absolute, the actual number. So this is strange because we don't have tables where there's H naught, just delta H. So here's a list, and what we're going to do next is we're going to look at some trends. This is part B. We're going to look at trends that we can glean from this table. For instance, you have a substance at different phases. Looks like the gas has more disorder, has a greater entropy than the liquid. Same thing here for sodium. The liquid has greater entropy than the solid. Oh, and look at the gas, sodium gas. So let me give you a couple trends. These are important because you may or likely are going to encounter questions that says which substance has more entropy, which substance is more disordered. Trend number 1, this is fairly obvious. Gas has greater entropy than liquid, than solid. But there are specific reasons for that. So the gas is due to greater molecular motion. And possible arrangements of atoms in a defined volume. Greater molecular motion and greater possible arrangements. Also, a gas compared to a liquid and solid, it takes up a greater volume. And previously we saw that larger volumes means greater entropy. So greater, per unit of, or per amount, if all of these are identical amounts. Number 2. Second trend is that for monoatomic comparisons, monoatomic comparisons, what am I talking about? For instance, sodium gas versus helium gas versus neon gas. Okay, they're all different substances. They're all in the same phase, but they have different entropies. This is based on molar mass. So for monoatomic comparisons, the greater the molar mass, spelling, the greater the entropy. And what are we comparing? Let's compare sodium, neon, and helium. Do I have a periodic table anywhere? My apologies. Oh, here we go. Greater the molar mass, the greater entropy. We have helium. Neon is 20 grams per mole. Sodium is 22.99. So it looks like sodium, I hope, has greater entropy when the phases are the same. Okay, here we go. Oh, thank goodness. Here we go. 153, 146, 126. So here we're going to say sodium in the gas state, greater entropy than neon in the gas state, greater entropy than helium in the gas state. And again, all same phases. That's essential for this trend. Number 3. Two molecules. If same phase and identical or near identical mass, then the one with higher complexity has greater entropy. The one with higher, and we have this new term, complexity. The higher the S entropy. Let me give you an example of that. Let's take oxygen, but we'll look at ozone. Ozone, you recall, looks like that. It actually has formal charges. One on oxygen, positive, one oxygen negative. And just for practice, put in your lone pairs. That will have a higher complexity than a molecule that has close to the same molar mass, but less complex, such as diatomic fluorine. It's not the charge that makes it more complex, it's literally the number of atoms and the number of different arrangements those atoms can take. Because this molecule here has more different arrangements, or how should I say this? Movements or arrangements than F2. Whoops. Than F2. And I am going to go to the next page to explain that. Those are your three trends, okay? Phases of the same substance, monatomic comparisons. I think this is the one that people tend to forget. So if you have monatomic species of different elements, you go by the molar mass. And then complexity, it's a little bit abstract, but with practice, we're going to know between two molecules that have the same phase and near or identical molar mass, which one's more complex. Let's take a look at some of those examples on the next page. So the next page represents topic C for the video. And I have a cartoon here. But how should we call this? We could call this either complexity or maybe molecular motions. Yeah, let's call it molecular motions. Now, we know that molecules, specifically gas molecules, they go in straight lines. So that's a motion. So here we have maybe argon, and we know it travels in a straight line. But other gas molecules, it doesn't have to be monatomic. They travel in straight lines. They bounce off each other with predictable force and angle. That is called translational motion, just straight movement. Translational motion. But what I'm interested in, especially when comparing molecules and the different complexities, I'm more interested in vibrations and rotations. So these are examples of vibrations. And these are rotations. Okay. And there are different types of vibrations. Some are called stretches, and some are called bends. And we'll see those specifically in just a bit. And there are specific type of rotations, mainly around the x, y, and z axes. This is what I mean by complexity. Which molecules have more vibrations? Which molecules have more different rotations? So here's ozone and F2, the example that we saw on the previous page. This fluorine mainly does stretching. And it could look like that, it could look like that, it could look like that. So what are these? These are different arrangements. These are different microstates, right? Like A, B, C, D, different microstates. But by adding a third molecule, yikes, by adding a third atom, now we get some bends. So these are stretches for sure. But these are, nope, down here, these are bends. This is still a stretch, right? Yeah, it looks like we're just stretching the bonds. But these are bends. Like literally, for instance, we're pushing outward like this, like scissors. And here, we're going to push inward. So we're making different bond angles. All the bond angles up here are identical. So bends change bond angles. By adding that third atom, we have access to more microstates. So again, it gets a little bit complicated. You got to visualize these molecules. I think it's pretty obvious that a 3-atom molecule has more complexity than a 2-atom molecule, and therefore has a higher entropy, S. Okay, S absolute. So, what do I want to say to sum this up? The more complex, more atoms, you'll get more vibrations and rotations. All of that points to a, therefore, greater entropy. Greater entropy. Large molecules. Actually, I never really explained what this is. This is a protein, right? A representation of a protein chain, and when it folds, it's actually getting more ordered. You are losing entropy in this case. The the number of different arrangements in a folded case is much, much less than in floppy, unwinded state. Okay, so that's one bullet point. What else do I want to say? You may hear the term degrees of freedom. The more complex you have, more, it's called degrees of freedom. It's just different ways to arrange the atoms. Equals the different ways to access different energies, different ways to arrange atoms. And along with this idea of degrees of freedom, this means more, we've discussed this before, more microstates. Okay. That's it for this video. Let me leave with one preview statement. Because in the next couple of videos, we are moving away from individual molecules and comparing individual molecules to each other. We're going to start looking at change of entropy in reactions. So as a preview, I want you to know that entropy goes up for a system when the temperature goes up or the volume, okay, when the volume goes up. I think that makes sense, right? When you raise the temperature and start to boil a substance, obviously the gas has greater entropy than the liquid. Or when you let that gas expand, we saw this in the previous video with a practice problem. When the gas expands, temperature is held constant, the entropy also increases. So entropy goes up for a system when the temperature goes up or the volume goes up, as long as the other is held constant. And that's all I want to say for that. Is there anything else? Yes. So in the next couple of videos, we will be starting to look at chemical reactions and how to predict entropy and how to calculate entropy, not of a system that changes its phase or changes its volume, but for a reaction, literal reaction, where we make different molecules as the products. How can we possibly estimate entropy in those cases? That will be in the next couple of videos.